not all taken in the same day. I couldn't have taken that much punishment in one day. A lot of fun. Any wakeboarders in the room? A couple wakeboarders? I've tried. It is definitely fun. One of the issues if you transition from water skiing to wakeboarding, when you slalom water ski, your body is oriented like this. This is the safe position behind the boat. When you're wakeboarding, the board actually needs to face the boat like this, and so your whole hips are oriented slightly differently. So when I was learning to wakeboard, it was difficult because this was my safe position, but this will have the board oriented like this, which will catch the lip of the board, and your whole thing, the whole body will go like this, as you saw several times in the video. What we are going to do today is we're going to analyze the force of impact on Mr. Palmer's face during one of these collisions. So you can see, in real time, it happens a lot faster. Right? I go from here to here.
How did it feel?
You know what? It's so much fun. That's what I'll say to that. All right. So our goal here today is to figure out the force of impact on Mr. Palmer's face. If you ask why, I will simply say because we can. I will also say service is a very good review of a bunch of stuff that we've learned in this class. Let's start out with just the general equation for force of impact. We need that in order to solve this equation. That's where we're going to start. General equation for the force of impact. Awesome. Force of impact. So many resources you should have with you.
Yeah.
The least of which is your brain. Or maybe the most of which. Hard to say. That's Gothard.
Changing momentum.
Change momentum over change in time. True, but what's that equal to? Change momentum over change in time is equal to. Sam. The net force. The net force equals the change momentum over change in time. This is because during a collision we consider all the other forces to be small enough compared to the force of impact that they are negligible. So the net force is considered the force of impact. What is the symbol for momentum? Crittenden.
It is momentum.
Yes, that is what I'm asking for. See why we review sometimes. It's just kind of fun. The symbol for momentum.
It is lowercase p.
It is lowercase p, not to confuse with uppercase p, which class stands for, or rho, lowercase rho, which is density. So the change momentum over change in time. The equation, or actually change in, is delta is always final minus the initial. What is the equation for momentum? Gentlemen? Not now. If you have questions, feel free to ask. But let's not work on that now.
I just want to know what rho is.
What rho? Okay, well then ask me. Because that, like, this is irksome. Rho, the symbol for rho, what does it look like? You start off from what?
Giant E.
No, a giant E would be sigma. Grimmer?
Symbol for rho.
Right, what does it look like?
Kind of like an E.
Kind of like a P. Okay,
Yeah.
so this is the symbol for rho. I'll just put it right here. Looks like that, and it's really hard to tell the difference on the board. It's a kind of a curly P as opposed to a lowercase p, and it stands for density. So that's your rho. Equation for momentum. Clay.
Mass times velocity.
Mass times velocity. So we have mass times velocity final minus mass times velocity initial divided by delta t. Okay, so let's walk through the variables here. Sim, this is the mass of what? Not quite, because this is the force of impact on Mr. Palmer's face, not the force of impact on Mr. Palmer. Subtle distinction.
So like your face.
The mass of my face is probably a little bit more than that.
Your head.
Right, the entire head. Okay, so basically we're considering my head to be an independent piece. We're just figuring out the mass of my head. Now, the internet is an amazing place. You can find all sorts of stuff hidden there. For example, from the Department of Anatomy and Histology at the University of Sydney, we have a quote. An adult human cadaver head cut off around vertebra C3 with no hair weighs somewhere between 4.5 and 5 kilograms, constituting around 8% of the whole body mass. So we are going to consider the mass of my head to be approximately 8% of my total mass. So we're going to take 0.008 and we'll go multiply it by my mass, which is 68 kilograms. Therefore, we're going to get the mass of my head. It is, please. 5.44 kilograms. Okay, so we have 5.44 kilograms times the velocity final. Now, notice that this is during the collision. So let's take a look at moment by moment what's going on here. We're going to go frame by frame through Mr. Palmer adjusting his hair. Then he decides that he wants to turn a little bit. He turns, and you can see the board gets caught in the water right around here, and my feet essentially stop, and I go from vertical to horizontal. And right here is the beginning of the collision with the water. There, the collision is done. To review, this moment is right when I'm first striking the water. This moment is when I am done striking the water. That is when we're figuring out the force of impact. We, of course, need to deal with a couple of things here. Oh, wait, I'll go here. We need to, well, actually, let's start out with velocity final. What do we know? We actually know the velocity final during the impact. What is the velocity final during the collision, please? Michael? 0. Notice, after the collision with the water, my head comes to a complete stop in the water. You can see from here to here, if we were to move on, you'll see that my head actually stops right there. So we know velocity final is equal to 0, so we have 0 right here, minus 5.44 times the velocity initial divided by the change in time. So we need two more things in order to solve for the force of impact on Mr. Palmer's face during this collision. We need the initial velocity during the collision, which is going to be physically right there. There it is. Right as my face is starting to strike the water, and we need the change in time during the collision, which is while my face is striking the water. One of the things we also need in order to solve this, in order to solve for this velocity initial, is the velocity of the boat. The boat was moving at about 25 miles per hour. Let's convert that over to meters per second. 1 hour, 3,600 seconds. 1 mile is 1,609 meters. Miles and hours will cancel out. We'll get the velocity of the boat, please, in meters per second. Please.
11.1
Meters per second. Okay. Now, this is going to seem a little bit odd when I do it, but it's going to make sense when we get all the way through. We are going to assume that I'm actually not moving. What's truly happening is I'm moving along at the same speed of the boat, and then suddenly my feet stop and my body does this, right? But we're going to separate those two motions. We're actually going to first just talk about going from vertical to horizontal. From vertical to horizontal. Then we're going to add the velocity of the boat. So for a little bit, we're going to ignore the velocity of the boat. We're going to pretend I'm simply standing there at rest when suddenly the boat pulls me and I go from here to here. Okay? That is circular motion. We are going to assume that this circular motion is U Fishy M. It is not perfectly U Fishy M, but it is close enough. Maria, remind me, what does U Fishy M stand for? You missed a Lee in there, but uniformly angularly accelerated motion, U Fishy M. Uniformly angularly accelerated motion works just like uniformly accelerated motion. In that class, there are how many variables?
5.
There are how many equations?
4.
If you know how many of the variables,
3.
you can figure out the other.
2.
This leaves you with 1.
Happy physics.
Happy physics student. Very nice. So, Oh, let's just review the 5 U, Fishy Em variables. We need to figure out 3 of them, but let's remember what the 5 were for us. What are the 5 possible U, Fishy Em variables?
Well, there is the fishy, which is
Bless you.
angular acceleration.
Angular acceleration is 1. It's good to review sometimes, isn't it?
Right, yeah.
Ian, help him out.
Angular velocity.
Angular velocity, initial or final?
Initial. And
Well,
final.
and final. That's 2 of them, right? Angular velocity initial, angular velocity final. That leaves us with 2 more, Hunter.
Changing time.
Change in time, and last one, Sean.
Angular displacement.
Angular displacement, change in theta. So those are the 5 U, Fishy Em variables. We need 3 of them. Hoover, tell me one that we know of the U, Fishy Em variables.
Velocity final.
We actually do not know angular velocity final. Angular velocity final is actually what we're trying to find. Let me just point out that one of the things that you need to make sure you're aware of is we're now talking about the circular motion, which is from here to here. So the angular velocity final would be the same as the angular velocity initial during the collision. So there's 2 subtle distinctions there between part 1, essentially, and part 2, the collision. Monsieur Laframboise.
We know time.
We know time. Well, we could see it in the video. We haven't figured it out yet, but we can figure out the change in time in terms of number of frames. So we can count through the number of frames here. So we're going to go backwards. If my computer can do it, we have 1, 2, 3. It's amazing how slow this is. 4, 5, 6. Did it do it? 7. There we go. And the last one, 8. It's usually 8 frames. There we go. 8 frames gets us to I am completely vertical, which means I have 8 frames from when I go from vertical to horizontal. This is 1998, so this is standard definition NTSC video. Class, what's the frame rate of standard definition NTSC video? We've gone through this before. It's 30 frames per second. What about high definition? 60 frames per second. It's okay, you don't have to have that memorized. I don't know why you would. I do. So this is 30 frames per second, so we have 30 frames on the bottom and 1 second on the top. This gives us frames cancel out, and we get 8/30ths of a second. So just less than 1/3 of a second is the time that I have for my brain to say, oh, I'm falling. You might want to prepare for the collision with the water by like closing your eyes or something like that. Just less than 1/3 of a second. So far, we have a change in time. We need 2 more U, Fishy Em variables so that we can figure out the angular velocity final. Tristan?
Angular displacement,
Is?
90 degrees.
We know the change in theta, the angular displacement, is 90 degrees. I go from vertical to horizontal, which is 90 degrees. We need that in terms of radians, so 360 degrees on the bottom, 2 pi radians on the top. Degrees cancel out, and that is pi over 2 radians, a number that probably many of you already knew. 90 degrees, pi over 2 radians. Change in theta. 1 more. Got there.
The angular velocity initial is 0.
Note, remember what we were doing? We were separating the circular motion from the linear motion. We're saying that I'm simply at rest to begin with, so my initial angular velocity is 0, and I'm going to accelerate through U, Fishy Em. So yes, the initial angular velocity is equal to 0. So now what we need is we need a U, Fishy Em equation that relates angular velocity initial, angular velocity final, change in time, and the angular displacement. I will take it from whomever has it. Please. Please square it, grammar.
Delta angular displacement equals 1/2 times angular velocity initial plus angular velocity final times the change in time.
Great. We have the angular displacements in terms of angular velocity initial, angular velocity final, and change in time. We could solve for this angular displacement with pi over 2 radians equals 1/2 times the angular velocity initial, which is 0. Angular velocity final, which is what we're solving for, times the change in time, which is 8/30ths. We can take out a 1/2, we can multiply by 30 over 8, we get that the angular velocity final is equal to 30 pi over 8, and that's in radians per second. We could multiply through and figure out what the number is, but at this point it's kind of irrelevant as to what that actual number is. So, let's multiply through. Let's get omega final, please. 30 pi over 8.
11.7809.
Great. Actually, does it work out to be 1, 0? I believe it rounds.
7.
Right, so it's going to round to 1, 0. And that's in, again, radians per second. Okay, so that is the final angular velocity. But we actually need this in terms of a linear velocity. So we need the tangential velocity. So how is the tangential velocity related to the angular velocity? Please. Tangential velocity is related to the angular velocity. How?
The radius times the angular velocity.
The radius times the angular velocity is the tangential velocity. So technically this is the tangential velocity final is equal to the radius times the angular velocity final. Physically, where is the radius in this problem? The radius goes from what point to what point, Grimmer?
From your feet to where your head lands.
Right, so we're going to say to the middle of my face, and technically it's not from the bottom of my feet, but rather from the middle of the wakeboard, right? So we need to go from the middle of the wakeboard to the middle of my face. This is a distance that I have measured out for us. This distance is equal to 1.66 meters. Distance from the center of the wakeboard to the center of my face. So the tangential velocity final is equal to 1.66 times the angular velocity final, which was 11.7810 radians per second. The tangential velocity final. Please.
$19.5564.
19.5564, and that's in meters per second. What is the direction, Hoover, of this tangential velocity, this final tangential velocity? You can't get it from the equations, you just need it from physically what's going on. Down. Notice at that particular point, my face is going straight down. So this is the final velocity in the y direction. And this is where we bring back the velocity of the boat. Because what we just figured out is the final velocity in the y direction, but I'm actually continuing to move in the x direction, and my final velocity in the x direction is going to be equal to the velocity of the boat. We're going to assume in the x direction that I'm still moving at approximately the same speed as the boat, which is a good approximation. We can figure out the final velocity, which is going to be along the hypotenuse. What are we going to use to figure out the final velocity here, please, for us?
We are going to use the Pythagorean theorem.
Pythagorean theorem, we're going to say c squared equals a squared plus b squared, therefore the final velocity squared equals the final velocity in the y direction squared plus the final velocity in the x direction squared. Therefore the final velocity equals the square root of the final velocity in the y direction squared plus the final velocity in the x direction squared. The final velocity is going to be equal to, final velocity in the y direction is negative 19.5564 squared plus the final velocity in the x direction is just the velocity of the boat, 11.7 or 1736 squared, the square root of that whole thing.
$22.5234.
22.5234 meters per second. That is the final, or actually technically the final speed of my head. We could figure out the angle. It's kind of irrelevant here. We don't really care too much about what the angle is. We could go through and do that just using the tangent theta.